So, okay, got it. Yeah. So one of the things is that we know from different observations that the universe is expanding. Okay, I think you have already had some experience before that the universe is expanding, and therefore the distance between two objects increases. Okay, and the farther they are, the rate of increase is higher. All right, so it is written as kilometer per second per megaparsec. Okay, so if the two galaxies are 1 megaparsec, then the recent known value or estimated value is of the order of the H naught, what we popularly call, is of the order of 67 kilometer per second per megaparsec. So two galaxies that are separated by 1 megaparsec recede from each other in a speed of 67 kilometer per second. Okay, so if they are farther, the speed will be faster. Okay, so the spectrum of the emitted light gets red shifted. All right, so if some light has been was emitted in the blue frequency, it will come to you in the redder frequency side, right? And what we can do is that, so we can understand that the distant the sources are, the more stretched will the wavelengths be, so Z will be more. So therefore, redshift Z can be used as a coordinate. There's a schematic diagram of that. So I'll leave it to you to have a look after the lecture, that how this happens. So here is a calculation. If anybody doesn't, okay, so let me ask a question. If you do not know the Friedman-Robertson-Walker cosmology, I'm sorry. If you do not have an exposure about the Friedman-Robertson-Walker universe and the homogeneous and isotropic universe, you can let me know now. If not, then I'm going to assume, I mean, that everybody knows that, but there is, I mean, nothing harmful in saying that if you don't know the Friedman-Robertson-Walker universe and the metric in that. No, so everybody knows that. All right. So for example, as you know that the ds square in the Friedman-Robertson-Walker universe is written as plus dt square minus a square t dx square or dr square, the coordinate system that you are going to choose, either Cartesian or spherical polar in the spatial part. So you can see that this is and here, if you take curvature, then there is a square root of 1 minus kr square comes in the denominator. And here it is showing that if the two rays, for example, light rays are emitted from one star, let's say, and the universe has been expanding ever since. So the place is the same, R1, the distance from the Earth is the same, let's say it is R1. So the light rays are emitted at T1 and T1 plus delta T1, okay? So, and then they come to Earth at present time. So you can do these calculations. I'm not going through the detail, and the time difference, this delta TE at the time of emission and the reception, you can write it as, you can equate it as delta TE by AT, the scale factor at the time of emission is equal to the delta T0 by A at the time of reception. So then it can simply give you the formula that this delta T is related to the frequency and frequency is related to the wavelength. And thus you can write this lambda 0, the wavelength of the observed wavelength with respect to the emitted wavelength is equal to 1 plus z. Okay, and that also gives you the scale factor of the universe as A equal to AT0 and ATE. For most part of the lecture, I'm going to assume that AT0 is normalized to 1. Okay. So here there will be some kind of assignments. So for example, plot the age of the universe as a function of redshift. So I will be giving, so just keep in mind that you have to do these things after tomorrow's class. So I will not be checking those assignments, but this is for your own benefit. So I will be sharing the IPython notebook. So using that, you need to make the age of the universe as a function of redshift, and you have to plot that. Okay. Now, the time from the Friedman-Robertson universe, the element of time dt can be written as dx divided by this Ez. We call it Ez usually, this denominator, and where x equal to 1 by 1 plus z. And if you write it in terms of the redshift, it turns out to be minus dz by this term, the Ez. Now we would like to know the distances. Okay, distances using radial coordinates. It can be simply written as RZ equal to integration of dt by at. And it holds true only in the flat case. So if you go to the non-flat case, let's say curved universe, where the universe has curvature, positive or negative, you can write it as like this formula, and which boils down to this formula afterwards. You can find the reference. This formula will coincide to the Weinberg's cosmology's discussion. So you can, they are taken from that book. So you can have a look at that book, Weinberg's Cosmology. It's not the gravitation and cosmology, it's a Weinberg's Cosmology book. Okay. Okay. Now we can define different types of distances. Okay, they will all be defined in that notebook that I'm going to share tomorrow. So distance between two simultaneously occurring events where the dt equal to 0 and d theta d phi equal to 0. Let's say we are talking about radial distances, can be written as this, and this st, the proper distance, is written as at times r, and this r is what we have discussed here. All right. If we take this a factor out, then it comes, then it is called as co-moving distance, right? Where you have factored out the expansion of the universe. Now let's talk about the horizon. Horizon means that in simple terms, let's say you are here and you are trying to see what, trying to understand how far you can see. Okay, let's say you have the ability to see everything that is there in the universe, but there is a limit, because light takes time to come from one place to another. Okay, so if the universe is infinitely big and infinite, if the universe was forever present, then light, even if it is infinitely large distance, if you are talking about infinitely large distances, light would have taken infinite time to come to you, and then your horizon would have been infinite, right? But we know that the universe at the beginning, at the time of Big Bang, 14 billion years ago, that you are going to compute. You have already computed, or you are going to compute tomorrow with me. So in those cases, light takes some time from one place to another place to come, and it cannot, in every case it happens that light takes time to come, but you can only see a part of the universe. Okay, not the whole universe. If the universe is infinite, but it had a finite starting point, then you can only see a part of the universe. What is that? Is that the part of the universe is can be equated to the c times t. Okay, c means the speed of the light, and t is the time since the beginning of the universe. Okay, so but actually the visible universe, that we can think that this is our visible universe, c times t, it is much larger than that, because the universe has expanded. Okay, universe has expanded ever since. So the star that had emitted light, let's say 100 years ago, and it is coming towards you and reached you, now that star is farther apart from you. Okay, so I'm just giving you a very simple exaggerated example, but you can understand from that the star is there, and the light is coming, and by that time the star has moved away from you, so your horizon increases. Okay, so how you can calculate the horizon? It's calculated like this: our horizon, and from 0 to today, where time equal to 0, and at any point of time you can calculate the horizon by saying that RT equal to integration of 0 to t. Okay, and the co-moving horizon is just without the scale factor. Okay, and when the scale factor is 1, which we normalized today, so then the co-moving and proper horizon are same today. Horizon today is 14.26 gigaparsec. Okay, which is 46.5 billion light years. All right, so you can understand that this is much more than light would have. It is much more than light travels within 14 billion years. All right. Now, co-moving distance is the distance between the objects in a space where it doesn't expand. And again, the reference, as I said, will be from the notebook. This is the plot that I had done. So, for example, this is the redshift, and we are here today, and we are going to very high redshift, let's say 10 power 4 or something like that. All right. So you can see that the co-moving distance goes increases as you go back in time, and then it becomes nearly constant, right? Then there are different types of distances which comes in handy in doing different types of calculations. For example, angular diameter distance. Let's say there is a size. There is a size associated to a source of light. Let's say a galaxy is emitting light, which has a diameter of d, and it is the plane of the galaxy is perpendicular to the line of sight. All right. And it is taking some time to come to you. And at the radial distance r1, the time is t1. So the proper distance between the two ends can be written as a r1 d theta. So usually it should be r1 d theta, but since the universe has an expansion factor, we have to factor that in. The angular diameter distance is written as this d by delta theta. All right. So which is a t1 times r1, and you can also write it as r1 divided by 1 plus z1. The full calculation for the full expression for for a curved universe, for a general universe where curvatures are allowed, it is written as this, where this sk factor can be sine x, or sine hyperbolic x. All right, depending on the curvature of the universe, whether it is closed or open or flat. All right, and dA of z is not a strictly increasing function of z. All right, so if you have any question of that, why it is that, then you can stop me. So as you can see that it increases and then decreases afterwards. So which says yes.
Sir,
yeah.
Sir, can you please explain that part? Why is it first increasing and then decreasing?
Okay, so yeah, let me go to this slide and then I'm going to tell you. Okay, so objects at higher redshift appear to be larger than they are. All right, that is why it decreases. Why they are larger? Let's say there was a galaxy, let's say a few years ago, okay, few 100,000 years ago, or let's just take some unit, and it had emitted light. Okay, two ends of the galaxy emitted light. So they are coming towards you. By the time they come towards you, so let's say it was at a time of matter-dominated epoch. I hope that you understand the radiation-dominated epoch, matter-dominated epoch, and dark energy-dominated epoch. If not,
yes, sir.
stop me again. So by the time they come to you, the light would have traveled far. Okay, and the galaxy's image, the two ends of the light, has also gone farther from each other. All right. So if you look to much larger distances, the object will appear as larger. This is an apparent increase, okay, that you are seeing. So that is why what happens is that the d theta. So what happens is that it is if d theta leads to a minimum d theta at the z peak, there is a peak. All right. You can find it when you calculate it. Okay, tomorrow I'm going to give you that notebook as I promised. And for the baseline best fit cosmology, this z peak is 1.5. all right. So after that, the redshift of the objects appear to be bigger than the proper size. For up to 1.5, if you go further and till 1.5, if you go further and further, you will see that the objects are getting smaller and smaller. Then after 1.5, you will see that it becomes larger and larger. All right. So this is basically what happens is that why there is a peak, because the universe changed from an decelerated expansion to an accelerated expansion. So if you do the calculation, you will find that up to certain point they will start to increase. Okay, and then after, they will decrease, but after that they will start to increase. All right. The dA is going to increase, but this is not a very good measure of distance, because you need some distance that increases as you go back in time. All right. For example, here, as you have seen, that it goes and nearly freezes at some point. All right. So it doesn't increase much. Let's say I'm talking about supernova. I'm trying to understand supernova. Then this kind of distances are not very good. These are very good to understand the sizes of the objects and do lensing and this type of analysis. But here, these distances are not very good to use. All right.
Sir, one more question.
Yeah.
As you said that transformation from radiation dominated to matter dominated and to dark energy dominated. The redshift that from the current value of the omega m and other values, it was around 0.6. Z is equal to 0.6 for the 0.7 for the matter dominated to dark energy dominated, and
it's of the order of 1. Yes.
Yeah, And it's different from that value that we are
No,
getting.
this is no. I'm not saying that it is just exactly at the dark energy transition. Okay, so
Yeah, okay,
what I'm
okay.
saying is that it is the full calculation is going to show you that after this Z peak, you will start seeing a fall of the DL. Okay, so it is not exactly equivalent to that. Okay, so
Okay.
so it has all the factor. For example, when the matter dominated era was there, then even at that point of time, some type of dark energy was there. Transition basically means that when basically they are of the same density, right? But
Right.
now let's say the matter is of the order of 30% and dark energy is 70%. At some point of time, matter was 70%, dark energy was 30%, but the dark energy was also there and was contributing to the
Yeah.
to the expansion of the universe, right? So the universe was expanding. At some point of time, it gradually, it doesn't decelerate. There is a it is not like a discontinuous shift. There is a continuous shift. The universe was decelerating. Then after that, the rate of deceleration decreases, and then it goes to zero, and then it starts accelerating. Okay, so that's where the Q changes. So I will see if I have a Q plot as well as it changes. You will see that it is a smooth plot from radiation dominated to matter dominated to dark energy dominated. So this Z peak takes, it is a numerical calculation that takes care of everything into account. Okay, so that takes into everything account. Okay,
Okay,
all
sir.
right.
Sir,
Uh,
sir,
yeah,
one more doubt.
yeah.
Currently, universe is accelerating or decelerating?
Now it is accelerating.
Accelerating.
All the present observation points out to that the universe is accelerating.
Okay, so it means that if you go in the past, then initially it was deaccelerating and then accelerating.
Sorry,
Then shift. I
tell
just
me.
heard that jet peak around 1.5. Can you
Yeah.
say that? Can you say that it's like in the before that it was deaccelerating and after that it was accelerating in time?
No, if you go forward in time, let's say this is the beginning of the universe and the universe is expanding. Okay, so forget the keep. So we have been decelerating, but still expanding. Decelerating is still expanding. Here, the matter dominated starts. Decelerating, still expanding. Then we have started accelerating. Okay, so
Yes, sir. Yes.
okay,
Understood.
so
Thank you.
what you need to do is that you need to change the matter density and radiation density in that code, and you need to see what happens for the Z peak, for example, as in this assignment. And you can also calculate the Z peak for the curved universe for both types, +1 and -1. There you have to do some extra things in the code, but you will be able to do that. All right.
Okay, sir. Thank you.
Now it comes to the luminosity distance. For example, it is one of the most used distance in the literature because this is the distance that increases with time. You know that if energy is emitted from a star, let's say, then the luminosity, so if the luminosity is L, then the flux or the intensity that you are going to see at any point, that is distant from the star, are going to decrease. Why? Because it has to cover a greater surface area, okay, as they move away from the stars. So the surface area is given as 4 pi r square, and therefore the intensity per unit area decreases as 1 over r square. All right. So we need something that behaves like this, so that we can understand that if there are certain standard candles means that there are certain stars that have the same brightness. All right, the same brightness, we can see their brightness today from Earth, and we can simply say that okay, that star is at that redshift and at that distance from us. Okay, so it is a measure. All right, and if that doesn't match, then we can understand from the properties that whether the universe is accelerating or decelerating. All right, so okay, and there are these relations that this luminosity distance is the co-moving distance divided by a of z, and this angular diameter distance divided by a square of z. All right, so these are the relation between the distances. If you plot all of them together, as I said, this is the angular diameter distance that simply goes down, and there is this co-moving distance that stays simply flat after some time, and then the luminosity distance increases. Okay, then you can also calculate the angle subtended in from one point to one surface towards you. Okay, so that means this is also supplied in the code. So let's say this is the Big Bang, all right, and there is a place that is we call cosmic microwave background. All right, let me give you a simple idea of that. Initially the universe was radiation dominated, but matter was also there. As the universe started expanding, the radiation domination decreases because the radiation density drops down as 1 over r power 4. Okay, and the matter density decreases as 1 over r cube. All right, so radiation dilutes faster, and at some point of time the radiation started decoupling with matter. All right, so the mean free path increased, and we are going to discuss that in the CMB course, but I need this discussion here. So what happens is that at some point of time the photons stopped interacting with matter and then started streaming freely towards you, towards us. Now let us calculate the distances or calculate the angles. So I have exaggerated this image. This angle, so for example, this angle should be 45 degrees. So I'm trying to draw the light cone. Okay, so from Big Bang, so let's say this is the Big Bang surface or the beginning of the universe. Here, if you draw a forward light cone, this is the causal area. That means that from Big Bang, only this part was in causal contact with each other. All right, in the CMB. And if you draw one, let me see if I can get. Okay. If I draw one line from here to here and here to here, this is going to be again 45 degrees. So that gives me my linear dimension to this cosmic microwave background. All right. So this is the last scattering surface. You can also call it last scattering surface. You can also call it cosmic microwave background. So as you can see, the cosmic microwave background, at the cosmic microwave background, only this part from the Big Bang could be in causal contact with each other. Any 2 points. For example, this is the furthest point that could have been in causal contact with each other. And the angle that it subtends to us is of the order of 1 degree. Okay, it is, I think, is exactly 1.3 degrees or something like that. We are going to again calculate. This is of the order of 1 degree. But if you know, CMB is actually a surface which which we can see as remarkably of same temperature. So CMB temperature, if you look at a different direction, you will see that they are of the same temperature of the order of 2.7255 Kelvin. And the differences that comes are in the order of microkelvin. Okay, 1 part in a million. So the question is that how could this total area have the same temperature? For example, if you have the same temperature of a kettle, let's say you try to warm some water in the kettle. Initially, they will not be in the causal contact, not be in the thermal contact with each other, all parts. But at some point of time, the heat is going to be circulated in that water, and at some point of time, the water will have the same temperature. That is what is happening here. They must be in a causal contact with each other at some point of time. All right. Otherwise, there is no reason that this point and this point have the same 2.7255 Kelvin temperature. All right. But this is saying the causal contact, the area of causal contact is only this much. And the angle that you are looking at it is only 1 degree. All right. So this is the famous horizon problem, or the standard problem of a Big Bang cosmology, standard Big Bang cosmology's problem. So if you have just radiation, matter, and dark energy dominated era, you cannot explain this problem. You cannot get rid of this problem. All right. We are going to basically discuss this in more detail. Here there is another picture describing the same. So this is the Big Bang surface, and this is the cosmic microwave background. What I am plotting here is basically the fluctuation in the cosmic microwave background. But actually, if you look at the cosmic microwave background in the Kelvin order, you will see that it is of the order of 2.7255 Kelvin all the way. All right. So
Excuse me, sir.
yeah.
Sir, in the last slide,
Yeah.
where the Yeah, this part where it we can say that in causal context. What is the scale of that observation? Like we are observing the temperature of that area and saying that it's equal, and we can say that it's causally connected. And what is the scale of that temperature, like error? Because what is
I,
the error of the temperature, like standard deviation?
Oh, error means what you are you talking about the instrumental noise, or you are talking about the fluctuations in that physical fluctuations?
Fluctuations.
Physical fluctuations that are here,
Yes,
for
sir.
example, the physical fluctuations are of the order of microkelvin. All right. So as I said,
Microkelvin.
it's 2.7 to 55 Kelvin. So that is the mean
Okay.
temperature. It is precise up to that point, and then there are microkelvin order fluctuations. All right. That fluctuations also has a coherent physics, that has a correlated physics inside, that we are going to discuss
Yes,
in
sir.
the third lecture. Okay.
Okay, so
So
as I have a doubt that as you are evolving from that instrumental, we are developing our instruments and getting better and better pictures.
yeah.
Initially, we saw that the whole cosmic CMB was at the same temperature, and after that, when we developed W map, then it was a little variation, and in Planck there was more variation. Like, and if we develop more better instrument, then what will be that area, that 1
Okay.
degree?
No. Okay. Yeah. Okay. Good question. But this is a wrong perspective. Okay. Uh, it is not that when we had Kobe, then WMAP, and then Planck, we had more fluctuations. The fluctuations were same. All right. Now the thing is that we didn't have that much resolution power. So I am going to show some photos in the CMB lecture, CMB lecture, where we are going to discuss what. Okay, I think I have some here as well. Okay, what happens is that, let's say, think it as like a TV. All right. So you had the standard deviation TV, and you had then high definition TV, then you had 4K ultra high definition TV, right? So what happened is that the people haven't changed, right? The photo, if you look at the photo of a people, the people haven't changed. I mean, if you look at any photo, let's say, okay, let's not talk about people. Let's try to have some example. Let's say you are photographing a grass from a helicopter, all right, in a field. So if you just if you were doing in 1990 or 2000, if you have bought a TV there, then you would have seen that the grass is completely uniform. All right. The
Yes, sir.
grass had some flux, but the grass had fluctuations, right? There are some places there are grass and tall grasses, and there are some places there are short grasses. Now
Right,
you
sir.
come to 2010, you have like 2K TV, high definition TV, and you see that you can see those differences in a more accurate. Okay, so that means that if you take a 100-meter surface, or let's say 10-meter surface, you can see the fluctuations. But if you take
Yes,
1-meter surface, you will not see the fluctuations. Now you have ultra high definition TV in 2020. So now you take the picture and project it on your TV, and you will see that even at 1 meter, you are able to see the fluctuations in the grass. All right. So this is
yes, sir.
exactly what is happening. So we had lower resolution power at that time. From the beginning, we knew that the fluctuations are of the order of microkelvin. So what happens is that they are of the, let's say you take a very fine map of microkelvin sensitivity. Okay, you take very high pixels, and then you rub it off. Then you basically take a cotton, and then you rub it off and you smooth them. Okay, so what happens is that your resolution goes bad. You will see that part smooth, but the fluctuations are all of the order of same magnitude. If you now take a small cotton and then rub it off, you will see that you can resolve some more. Okay, and if you don't rub it off, then you will see very precisely that even from one point to another point, you will be able to see the differences, right?
Yes, sir.
Okay, so they are of the same order. Okay.
Okay, sir.
Now let me give you an idea of the timeline. The timeline is from Big Bang to this last scattering surface is of the order of 400,000 years. And from there to here, you can simply approximate it as 14 billion years. All right. So what happens is that you cannot explain that this point and this point were not in causal contact with each other. As you can see that this light cone do not intersect at the time of the Big Bang. All right. But they should not have the same temperature. What happens is that inflation helps us in this regard. It takes the Big Bang surface little big, bit backwards. All right. And it says that the light cones, it makes room for the light cones to intersect. And why it is inflation? You just think that it is some kind of a some small ball, okay, some tennis ball, where all of the air had the same temperature. What you do is that you just say that you inflate that, you make you put lots of pump in that so that it becomes like a balloon, okay, a huge balloon. What happens is that that balloon, when it was a ball, had the same temperature, okay, now it had expanded, it now has the same temperature at all parts. All right, so the space has expanded, any 2 points has expanded in an accelerated manner, and this acceleration is of the order of exponential acceleration in time. So that is what we call as inflation, okay. So it is not just a normal acceleration, okay, it is an inflation. So that is how inflation solves this horizon problem. Okay, so let me just see what is the time. Okay, that's good. Now modes, let's talk about modes. All right, modes means, let's say we talk about wave numbers. Let's say you have the perturbations in the cosmic microwave background, and you break them into different modes, spherical harmonics, and then they are related to Fourier modes. And the Fourier modes, this k, you can relate to lambda. All right, this might look a little bit of, I mean, a little bit difficult, but when we are going to discuss the perturbation theory, we will get a hang of it. Okay, so the lambdas vary proportional to the scale factor. Let me do certain calculations. Okay, I did a mistake. Okay, I should have shared and just share. Let me just minimize and let's do some calculations. Okay, so let's draw some timeline. Okay, this is today, and this is Big Bang. Let's say this is radiation dominated. 400,000, that corresponds to a Z of nearly 11,000, 1100. So let me just write it as 1,000. Okay, this is radiation dominated ends. So I should, sorry. This is the CMB, or the last scattering surface. Okay, this is radiation dominated, this is matter dominated, and let's say this is Z of the order of 1. This is dark energy dominated. All right, so let's do some calculation. We know that at radiation matter dominated era, the A of T, the scale factor, anyone knows what is the form of A of T? Is it a power law? Okay, let's just assume that you know. It is a power law, A to the T by P. Sorry, T to the P. And so H is A dot by A. So which you can write it as P by T. And the horizon DH roughly is H inverse. So it is T by P. Okay. So, and the lambda T, lambda at any T is lambda 0 A of T, I'm sorry, by A0. Okay. So the lambdas grow smaller as we go back in time, and we can simply write this dH as well. T by P is proportional to A to the 1 by P. So if we take log of dH, right, goes as 1 over P log A. So if we draw a diagram of log dH and log A, it will be a linear diagram, right, with a slope of 1 by P. And what is the slope? So P is 1/2 during radiation dominated, right? So the slope will be 2, 1 by P. And matter dominated, it was 2 by 3. So slope will be 3 by 2. This is exactly what is happening here. So this one, you can consult this review, Professor Sriram Kumar's review in 2009. You can search Sriram Kumar review in the Google and it will come immediately. So I'm plotting the log of length scale and log of A, and the green line plots the different slopes. Actually, this slope has to be, yeah, as you can see, this radiation dominated. The sorry, green line is not the slope. The blue line is the slope, and you can see that this has one slope which is sharper, steeper. That is 1 over p equal to 2, and this is 3 by 2. All right, this is 3 by 2, and the modes are actually proportional. All right, that we had already calculated here. There, if you take the log lambda, they will simply be log A. They're proportional to each other simply. All right, with the slope 1, let's say, and then it just simply cuts through. That means at some point of time in the early universe, the modes were outside the Hubble radius or the horizon. Okay, so it goes outside. All right, so this is
just a small confusion.
Sure.
The radiation dominated era, doesn't it end before the epoch of recombination, like at the redshift of 1100? Aren't we already in matter dominated epoch? In the Jamboard, if you see,
in the Jamboard, what did I say?
In the Jamboard, at the redshift of around 1000,
yeah,
we are already in matter dominated, right? Matlab, radiation dominated and around like at the redshift of 3600 around.
The radiation dominated and matter dominated equality, if I remember correctly, it is of the order of 3000 redshift. Okay, so then matter dominated, you can simply say that that is when the matter takes over, but again, it's continuous, right? So it is not that the photons were not interacting. In some, it was, the matter was more dense than the radiation, but at some point of time, this large scattering surface is believed to be a time when the matter radiation completely stopped interacting with matter. All right, so equality happens at around z equal to 3000. But then,
so last scattering is like epoch of recombination, right?
The epoch of recombination also again another long process. So recombination also happens when the ionization temperature of hydrogen, right? So it started before the recombination was happening. So it is again a constant continuous process. So last scattering surface happened right after when the recombination was completed. It happens at around 1096 redshift or something like that. Right.
Okay.
So this is, they are of the order of same. I think one is 1050. So yeah, of both are of the order of 1100. Okay, so there is no clear-cut difference. For example, last scattering surface, again, as I said, I mean, it is some number where you can think that the photon stopped interacting with matter. You can give a particular mean free path to the photons and can say that, okay, after this, I call it a last scattering surface. Okay, but recombination started earlier. I mean, different part of the universe started recombining in clusters. Let's say at some point of no, okay, so clusters not in the sense of a cluster exactly, but a cluster, by a cluster I mean that it happens inhomogeneously. At some point it was recombining, at some point it was not recombining. So there was it is a continuous process of ionization and recombination. Okay, so this happens in the reionization as well. So when the universe starts to cool down, then the average temperature, the temperature decreases, and then you find the binding energy, they starts binding, and then there were also some photons which were immediately breaking those binding. Okay, but again after a few years, again what happens is that the photon didn't have enough didn't interact enough in order to or photons didn't have the energy enough to break the binding. Okay, that is when you can also say that the recombination has is completed. I think of the if okay, I'm going to share another plot in the CMB lecture where you can understand what was the electron density at the time when the recombination ends. So when the recombination ends, the electron density or free electron fraction was of the order of 10 power minus 4. That stayed there. Okay, so even free electrons were there at that point of time. till the time of the reionization, then it increased again. So recombination is something like you smoothly the free electron fraction decreases. Okay, earlier there were already free electrons because protons were there and electrons were there. So they started combining. So the free electron function decreases gradually. You can solve it by solving the thermal history of the universe. Then it stayed to 10 power minus 4. Then it stayed like that until the reionization, when it started increasing again. All right.
Okay, thanks.
For the inflation, we don't need such physics of reionization if we want to understand the horizon problem. All right. So let me see. So all right, and ds square, as you know, is dt square minus a square t dx square. All right. So if you define a eta, sorry, d eta, a eta times d eta equal to dt. If you define a conformal time, this ds square turns out to be a square eta d eta square minus d x square. What you can do here, as you can readily see, that you can draw light cones here now, right? So this is today, and this axis is eta axis. All right, and this is the surface of the Big Bang. This is the last scattering surface. So this is radiation dominated, it's matter dominated, and somewhere it was dark energy dominated. Not very important now. So as I had plotted earlier as well, this doesn't overlap much. Okay, the forward and backward light cone. So here, this A of t is proportional to t power p. What you can do is take it as an exercise to do this calculation. I'm not going to go through all the steps. So t runs from 0 to infinity, let's say, and a also runs from 0 to infinity, right? And for p less than 1, radiation dominated and matter dominated, let's say, your eta is also 0 to infinity. So eta is 0 here. So in order to make the radiation dominated, or sorry, the Big Bang area, Big Bang surface much below, where you can simply say that they had quasar contact, you need to make the eta go negative. So, okay. So for the solution of horizon problem, we need eta goes negative. This can only be done with p greater than 1. All right. So I'm not going to the detail of the calculation. You can try that. And p greater than 1 means that if you take a double dot, a dot is equals to p t to the power p minus 1. A double dot becomes p into p minus 1 times t to the p minus 2. So if p is greater than 1, as you can see, a double dot becomes greater than 0. So the universe has acceleration. All right. So you need universe to accelerate before the radiation dominated epoch. Okay. Okay, another thing is that you can write down that you can calculate the as an assignment, you can calculate the sizes of the linear dimension of the forward and backward light cone. So this one and this one. All right. And then you can compare. One more example is that what you need, let's say you have seen the plot here, right? That the modes are going outside the Hubble radius. What you need is that as you go back in time, I need this requirement. Go back in time means that I have taken a negative in the time derivative. All right. So that means that we are going back in time. This lambda by DH has to be less than 0. So at some point of time, lambda is going to come inside the DH. Okay, that is called the sub-Hubble region. So this is called the super Hubble region. Sorry. So the modes are inside the Hubble radius. So these are called sub-Hubble region. These are going outside. So that means these are called super Hubble region. Again, if I am able to make them come inside the Hubble radius, we can again say these are sub-Hubble region, and this is done by this formula. Okay, this is the requirement. Now what does it tell us? So I can just write d dt, simply lambda t, let's say at some point of time t. So it is lambda 0 a means at divided by a0. That is what we discussed, right? And this dh is h inverse, so that means it is simply h in the numerator. So it is a dot by a. So a cancels. These actually can come outside because these are constants. So lambda 0 and a0 today is less than 0. What does it give us? Minus ddt of a dot means that minus a double dot is less than 0. That simply gives us a double dot is greater than 0. Universe needs an acceleration. All right, we have found it both from here and here. Okay. And okay, so another thing is that there is a flatness problem, but I'm not going to discuss that. Okay, so you can have a look. The flatness problem says that if the observation, since we know that from the observations the universe is extremely flat, the omega k is of the order of 10 power minus 3. It is consistent to 10 power minus 3 from the recent observation. In order to have this flatness, if inflation was not there, then in order to have the flatness, this omega k had to be at the time of the beginning of the universe, at the time of Big Bang, it had to be of the order of 10 power minus 60. So this is a fine-tuning problem. It says that in order to make the universe flat today, it had to be nearly 10 power minus 60. Otherwise, if we had a 10 power minus 50, today's universe would have been, we would have been seeing a curvature of 10 power 10 or something like that. All right. So this is something that comes as another problem of the standard Big Bang cosmology, and it's called the flatness problem. So what happens is that when inflation happened, it basically made the universe accelerate, and the omega k, which grows as k divided by a square h square, h remains nearly constant during inflation, and a exponentially inflates. So what happens is that omega k goes exponentially below. So even if the initial condition, whatever be the initial condition of the universe, if inflation was there, it would have made the universe flat. Any question? No, right? Okay. So this is the scenario of inflation, how it solves the standard Big Bang cosmology problem. So this is, as I said, this is of the order of the slope is of the order of 2, and before that the inflation makes the h nearly constant. So you can understand what happens if h is constant. That means a dot by a is equal to constant. So you can see that the universe accelerates simply, right? And all the modes, this cyan, blue, and the green lines comes inside the Hubble radius at sufficiently early times. Okay, so this is the typical solution of inflation. Now, how you can achieve inflation is something that you have to understand. So the matter, you have seen that for matter, you basically have an expansion of normal matter, which is a W of 0. Equation of state of 0 has a effect on the universe, that can be characterized as a deceleration, and it still expands, but it is a decelerated expansion, as I said. And the T of T is of the order of the A of T is of the order of is proportional to t to the power 2 by 3. In radiation also it is t to the power 1/2. So no w that is greater than 0 can help actually here. Okay, and you will see that in the dark energy course that in order to achieve the acceleration today, or for example, if you have studied general relativity, you will see that the cosmological constant, if the cosmological constant is the candidate for the dark energy, then it has a w of -1. All right, so -1, it drives the acceleration today. During the inflation, similar thing happened, but its potential must follow certain specific criteria, all right, in order to have an exponential expansion. All right, so in that case, what you need is that you need a scalar field. The scalar field, for example, if you study quintessence, there also scalar field comes. Okay, the potential is a bit different. So there you don't have exponential expansion. So let's say I start with minus plus triple minus signature, right? And everyone knows the action principle of gravity, or let's say simple action of a scalar field. Okay, I guess everybody knows. So d4x square root of minus g half del mu phi minus v of phi, where phi is the scalar field. This is the Lagrangian, and v of phi is the potential. All right. The stress energy tensor T mu nu can be written as del mu phi del nu phi. Okay, so this is a mixed tensor. Delta mu nu half del lambda phi minus v of phi. And ds square for the background level is dt square minus a square t dx square. So phi, so as I said, this is I'm using my plus triple minus signature. Phi is a function of time only. Okay, we are going to assume phi is a function of space later when we talk about perturbations. So t mu nu can be simply written as the diagonal. Okay, let me just rho of t minus p of t minus p of t minus p of t. So energy density and pressure. So this is the stress energy tensor. All the other parts, these are 0. There are no off diagonal components. And if you calculate it from here, you will see as okay, t00, which is rho, is equal to phi dot square by 2 plus v of phi, and tij equal to minus p delta ij. So this is the t matrix, right? Is minus phi dot square by 2 minus v of phi delta ij. So p becomes phi dot square by 2 minus v of phi. All right. Friedman equations. You have studied Friedman equations, right? Where you connect the equation of the scale factor with the constituents of the universe, matter, radiation, etc. So h square is 8 pi g by 3 phi dot square by 2 plus v of phi a double dot by a minus 4 pi g by 3 rho plus 3p. If you are not able to follow this, just let me know. I'm going to describe again. But these are the relations that you can simply go back and check. So what I can do is that I can just write it as h dot plus 8 pi g by 3 rho minus 4 pi g by 3. So a dot by a is this. So I just write it here, rho plus 3p. This rho plus 3p becomes proportional to phi dot square. Calculate that. and then I find H, sorry, I should write it as simple H because curly H sometimes is written in the conformal coordinates. H equal to minus 4 pi G pi dot square H dot, right? Okay, for A double dot by A greater than 0, rho plus 3p has to be greater than 0. So phi dot square has to be less than p of phi. All right. That means the scalar field's kinetic energy has to be less than the potential energy. All right. So this is called a slow roll. And the equation of motion, if we want to derive, is h square equal to again 8 pi g by 3 rho. That means phi dot square by 2 plus v of phi 2h dot. I take the derivative with respect to time is 8 pi g by 3 by. Okay, so I would ask you to do this calculation with me because these are important. Twice phi dot phi double dot by 2 plus dv d phi, which I write as v subscript phi and phi dot.
Sorry, sir. Interruption for sir.
Yeah.
That is 2 phi dot, na? Not 2 phi dot phi double.
So this is 2 phi. So this is
Oh yes, 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 yes. Yes, correct.
phi dot square. Okay. So this 2 cancels afterwards. All right. So this is minus twice h again. This is, you can write it as 4 pi g phi dot square equal to 8 pi g by 3 phi double dot plus v of v dv d phi and phi dot. I can simply cancel this from here and here. What I end up with is phi double dot plus 3h phi dot plus v phi equal to 0. This is the equation of motion of a scalar field, background equation of motion of scalar field in terms of in presence of Friedman universe. Okay, in Friedman universe, where as you can see the expansion of the universe is factored in as h, the Hubble parameter. All right. So as you can see here, this is what I had summarized here is phi double dot plus 3h phi dot plus v of phi is equal to dv d phi equal to 0. And to satisfy the condition for inflation, as I said, is needed that rho plus 3p has to be less than 0. And for scalar fields, this reduces to the slow roll. But actually, the field has to be slowly rolling, sufficiently slowly rolling. Why? Because you need 60 e-folds. 60 e-folds means that the universe should expand from the initial scale factor to the final scale factor during the course of inflation by e to the 60. Okay. So that is called a 60 e-folds of inflation. So just a second. Let me see if I'm going to cover this. Okay. Let me see time. Good. Time. So let me introduce this concept of e-folds that will be later used as a concept of time. Just like redshift, here also you can use a concept that this is n equal to log AF by AI. So this is the initial point, and this is final point. This has to be of the order of 60. We'll come to this later.
Sir,
Yeah.
here you have written the natural log, right? Or
Yeah.
log based 10?
No. Yeah. I mean, e-folds is in terms of E, That is why
Okay,
it's
okay,
called E folds.
okay, sir.
So, okay, I'm making a mistake of is minus 4 pi g phi dot square. So, which I can write as minus 1 over twice MPL phi dot square. This MPL is 1 over square root of 8. So, this should be 8 pi g. And we take it as 1. We will use it as 1 in the tomorrow's class. Okay. All right. So, from here, I am not going to spend too much time. Let me just write the final answer. Phi t square root of 2 MPL. I think this is MPL square. Integration dt square root of minus h dot. So what you need is that you need the scalar field to roll slowly. That means that phi dot square has to be less than v of phi. But at the same time, you need the scalar field to roll slowly for a long time so that you achieve this 60 e-folds of inflation. Okay, so you do not, during the dynamics, you do not allow the scalar field to ever break the slow roll. All right, so that if it, let's say, I mean, if the phi double dot is large, but phi dot is small, at some point of time, that means that you have acceleration. At some point of time, it is going to break the slow roll. So phi dot square will be larger than v of phi. We do not want that to happen. That is why we start formulating certain parameters. All right, we call them as potential slow roll parameter. So remember, what I am doing here is all background calculation. There are no perturbations here whatsoever. Okay, so phi depends only on time. Okay, not on space. So potential slow roll parameters are written as h square, are derived as such, like this. H square is of the order of 8 pi g by 3 v of phi. As you have seen that I have not written as a equal to, because I have neglected the phi dot square term with respect to v of phi. And another thing, from the equation of scalar field, I can simply write as 3h phi dot is equal to minus v of phi. I have neglected the phi double dot term with respect to the other terms. Okay, it's not, sorry, sometimes I make this mistake that I say that it is v of phi, but v. So actually, this is the potential, and this is actually the dv d phi. All right, when it is written as a subscript. So, all right. So phi dot square very, very less than v, and v phi square by h square very, very less than v. So using this, we find. So you square this, you will get this equation. From this, you will find that MPL square by v phi by v square is very, very less than 1. This is one condition. And you write it as 2 epsilon v, where epsilon v is written as MPL square by 2 is v phi by v whole square. All right, and then you use the other equation, this phi double dot equation, that phi double dot is very, very very, very less than 3h phi dot. You will find that you can write 3h phi dot minus v of phi. So take the derivative. H is nearly constant during inflation, so I neglect the time derivative. Dot. So what we find is that minus v phi phi. We just calculate this by 9h square. We have to use all these equations here. 9h square. If you are not able to do that, just let me know. Okay, so this is something that you should try at home and get back to me within any of the lectures that I'll be giving. Okay, it's very less than 1. So that again, if h square is replaced with v, I can with v, then it is basically saying v phi phi by v is very less than 1, and I can define another term, delta v is equal to mpl square v phi phi by v. So these two terms has to be very less than 1. Tomorrow we are going to see another type of parameter, slower parameters, which are handy, more in hand, comes in more easy form, which is called Hubble slower parameter. But as of now, let's just work with this, and they have to be very less smaller than 1. When it becomes 1, then we say that the inflation has ended. Let's say we are using a potential v of phi as m square phi square. The scalar field starts rolling slowly. Here the speed increases and the epsilon v becomes very close to 1. When it becomes 1, the inflation stops.
Hello, sir.
Yep.
Can you please go back to the
Yes.
Sir, here in the left hand side, you have written 3h phi dot is nearly equal to minus v phi.
Yeah.
And then in the second step, it is 3h phi dot is nearly equal to minus v phi into phi dot.
No, this is, I'm taking the, sorry, time derivative. I didn't write a dot.
Oh, okay.
Okay, sorry. I mentioned that, I'm neglecting the h dot.
Oh, h is a constant. Okay, so
it is nearly constant. Okay, so, but I forgot to give this dot. I'm sorry.
Okay.
All right. So we come up with these two. Why we are discussing this epsilon? Because from here we'll be able to see that what is, if we take a potential, what is its initial value, initial field value and final field value. Tomorrow we are going to work with bingo. There we have to give the initial field value of a for a potential. Okay, let's say I'm using m square phi square potential or lambda phi for potential for a scalar field. You have to know what is the initial field value. Then you will be able to let the code run, and then you will see the inflation. First we'll work with the background, then we'll talk about perturbation. So let's say v of phi is v0 phi to the n for a power law potential, power law in phi, and epsilon v you can write it as n square by 2 mpl square by phi square. How you get this? You just replace this with using this formula. Okay, very easy. You can do that. And delta v is n into n minus 1 mpl by phi whole square. Okay, I should have written whole square here as well. So these are small when phi's are large. So in these cases, these models are called large field models. Okay, so it also shows that, but the large field model says the delta phi, the total duration of the inflation, whether it is large or very larger than m Planck, or it is very close to m Planck, Planck mass, that is the quantifier of a large field model of inflation or small field model of inflation. So there are different models of inflation, right? That can be proposed. I'm going to show at the end some models of inflation and their acceptability with the data. So the thing is that we understood that we need, the story goes as follows, that we need acceleration, we need exponential acceleration. For that, we need scalar fields. And for the exponential acceleration, we need certain type of potential. And those potential are classified into different categories. One type of potential is called large field model, and one type of potential is called small field model. So large field models, where the inflation, the phi initial to phi final, during the dynamics, where the delta phi, where the difference between phi initial and phi final, the path that the scalar field traverses, let's say, in the potential, is larger than, very larger than m Planck or lesser than m Planck. For example, in quadratic potential, we are going to see right now. All right. So as I said, epsilon v is equal to 1 when the inflation ends. So from here we can simply say when it is phi f, it epsilon v equal to 1. If we equate that, we'll find that phi f is n by square root of 2 m Planck. If n equal to 2, that means that if I am having m square phi square potential, phi f will simply be square root of 2 m Planck. So what is the initial value of phi for quadratic model? Let's say n equal to 2. I can simply say total number of E folds is log AF by AI DTH TI to TF. All right. Here insert these two formula. H square, use this two formula equal to 8 pi G by 3V, and use also 3H phi double dot equal to minus V of phi. Not sorry, dv d phi. All right. Then you will get it as minus 1 m Planck square phi I to phi f d phi v by dv d phi. Replace the values for the quadratic potential. By a couple of steps, you will be able to understand that this is 1 over twice n phi I by m Planck square, Planck mass square minus phi f by m Planck square. It will be 1 over twice n phi I by m Planck square minus n square by 2. Because we have already obtained phi f square, right? Phi f, what is phi f? Which is n by square root of 2. For n equal to 2, and capital N, the E fold is equal to 60, we need phi I square equal to 240 Planck mass square. I get phi I of the order of 16 m Planck. So we are going to see that tomorrow using the code. We give the initial field value as 16. You will see that the inflation ends nearly at 60 folds. Okay, we'll see that it is more, but I'm going to discuss why it is more. Okay. Okay, let me just also mention that there are large field models, there are small field models also that we are going to discuss in the hands-on session. But there are also two field models. All right, there are nobody said how many scalar fields are going to be there. There can be multi-field models as well. There can be non-canonical models where your kinetic terms cannot be written as del mu phi del mu phi. It is a function of del mu phi del mu phi. In those cases, you are changing the kinetic term of the Lagrangian. So those are called non-canonical models. You can solve those as well and get the perturbations. Okay, now if any one of you does not have an exposure of general theory of relativity, please let me know. Everybody knows general theory of relativity, the Einstein's equations. If not, let me know. I can simply say a couple of words and then go to this topic. Okay, so you know G mu equal to 8 pi G times T mu. Okay, the left hand side contains the geometry of spacetime. The right hand side contains the within. That means that the constituents of the constituents in that spacetime, right? So G mu can be derived from the metric. Right, so so if you have gone through the Friedman-Robertson-Walker universe in the first, I think if it has been covered in the first two lectures, then you know that for a Friedman-Robertson-Walker universe, if you equate these two, you will be able to get the Friedman equation. Okay, so just like what we did, that it is 8h square equal to 8 pi g by 3 rho. Okay, and then rho we knew from the scalar field, so we just wrote the value phi dot square by 2 plus p of phi. These are the this is the Ricci scalar, and this is the Riemann tensor. Okay, sorry, this is the Ricci tensor. So R mu nu rho sigma is the, sorry, I'm doing mistake. So you can write, what you would do is that you just basically write the ds square. From there you can write small g mu nu, the metric. From there you can get the Christoffel connections, and then you can calculate the Riemann tensors or IJKL, and then okay, IJK is usually used for 1 to 3, but let's forget that. And then from there you can do contractions, and you contraction of the indices, and then you find that g mu nu equal to r mu nu minus half r delta mu nu, and then this is equated to 8 pi g t mu nu. All right. If there are no perturbations in the metric, you can simply write it as dt square minus a square t times dxi dx. All right, dx square times delta ij, of course. And then if you have perturbations, how can you add perturbations into n plus 1 dimension? Let's say we have 3 plus 1 dimension. This is how you add perturbations. In the dt square part, you can only add scalars, right? So it is 1 plus twice a, I am writing. So this red ones are scalars, times twice a del I b, that means it is a divergence of a scalar, makes it a vector, and then you contract this to, see if I pointer, contract this I and I. You can have a true vector Si, right? Contract that, and you can have psi times delta ij in this dxi dxj part. Then you can have twice delta del I del j e. I am sorry that this I should be in the subscript, which is the grad square of E, okay, which is again a scalar. You can have divergences of a vector, okay, del I fj and del j fi, and then you can have a true tensor hij. So here you have 4 degrees of freedom. Here you have 2n minus 1 degrees of freedom. So if n is 2, then you basically you have 2, and here you also have you have n is 3 plus 1. You know how many components are there because it is a symmetric matrix. Now you have these many degrees of freedom, then you have coordinate transformation. All right, so if you write them down separately, scalar, vector, and tensor perturbations, and we are writing it as a linear order perturbation theory, okay, you are separating as scalar, vector, and tensor here. And since you have gauge choices, you will be able to find by coordinate choices, you can remove any 2 of the scalar perturbations. Will be focusing on the scalar perturbation and then tensor perturbation, because vector perturbations decays without the presence of sources. All right, vector sources, and scalar field doesn't create vector sources and doesn't source vector perturbations, so they decay down. So that are things that are important are scalar perturbation mostly. As you can see that we have A, B, psi, and E. All right, I can fix a gauge where I say that I put this B and E to 0, and I work with twice this A and psi. All right, so this is called a Newtonian gauge. All right, where A psi is equal to we write it as phi. Okay, another thing is that I have jumped a step where this, even if you have this A and psi, you will be able to find that there is a term A minus psi that is sourced in the stress energy part of the tensor, but that is coming as an anisotropic stress. So if in absence of anisotropic stress, this term A minus psi has to go to 0. So then you can equate A equal to psi. So in scalar perturbation theory, you only end up with psi equal to A equal to phi. All right. So we have these 3 equations that are equated from G mu nu equal to 8 pi g tu mu nu. The first equation is coming from 0, 0 component. The second equation is coming from 0 I component, and the third equation is coming from the ij component. You can combine all of them and write it like this. All right, write it as an equation of phi. So this is called the Bardeen equation, and this phi, the scalar, the potential, the scalar potential, is called the Bardeen potential. All right. I hope everything is clear. If anything is unclear, please let me know. I can stop and explain again. And here, as I was saying, that I was writing H as a script H sometimes, but script H is usually used for denoting the conformal Hubble parameter, where it is A prime by A. Prime means d d eta, okay, not d dt. So here, as you can see, that this is depending on all these values. Cs square is written as P prime by rho prime, where P is pressure and rho is energy density. This is the adiabatic speed of perturbations. Okay. Then you defined a convenient quantity which is called curvature perturbations. All right. What does curvature perturbation do is that you write it as a combination of this H and phi prime and phi, the Bardeen potential and its derivative, and the conformal Hubble parameter. So if you replace that in this equation, in the perturbation equation, you will find that according to the Bardeen equation, the R prime behaves like this. All right. Important thing is that this is the non-adiabatic pressure perturbations. Okay, this is the adiabatic, as I said, speed of perturbation. The rest part is called non-adiabatic pressure perturbations, which does not exist in ideal fluid case. Okay, for single scalar fluid case, it goes to 0. And see, what happens is that only Ca square times grad square of phi remains. Grad square, if you go to Fourier space, becomes minus k square. All right, so you write it as k square. Now, in the super Hubble limit means that when the lambda, your modes go outside Hubble radius. Remember, this k now becomes important, right? Now this k, you can equate it as 2x pi lambda, and lambda is what? These are these lambdas, these perturbative modes. Okay, so as you can see, during some point of time during the inflation, they were at sub-Hubble radius, sub-Hubble stage. After that, it goes to super Hubble scales. When lambda is large, that means k is small. All right, twice pi by lambda. So when k goes to 0, then you can, let's say, it is of the order of 1 over h. All right, during inflation, let's say this h and h square cancels. H prime, let's say, it is nearly constant. So h and h square, so it's cancelled. So it is basically k square by h, like that. So you can say that if k is in the super, so if we go in the super Hubble region, if k tends to 0, we have r prime equal to 0. This is a very important point in the theory of inflation, that it says that if I start to solve the perturbations equation from here, I do not have to solve it entirely up to this point when these modes comes to the radiation dominated epoch and enters the horizon. I can simply see when the modes become super Hubble, when k tends to 0 or k becomes very when lambda becomes very large, k becomes very small, I can simply say that I stop my integration here. This is the super Hubble scales. Okay, initial, and this is the super Hubble scale. I stop my integration here at this epoch. All right, I don't have to calculate them at the end of inflation. That means r prime becomes 0 and r becomes a constant. Right, the curvature perturbation freezes. Right. So using the formula of delta p na, as I said, r prime becomes this, and then if you neglect this delta p non-adiabatic, you can find this. Plug them back in the Bardeen equation. The equation for curvature perturbation, r is called curvature perturbation, as I said, looks like this, where z is defined as A phi prime by H or A phi dot by H. In Fourier space, you find R double prime K. If you just write R as Fourier modes, R double prime K, Y Z prime by Z, R K prime plus K square R K equal to 0. Now I define another variable V, such as V equal to R times Z. All right. After substitution, we get V double prime K plus K square minus Z double prime Z times Vk equal to 0. This is called Mukhanov-Sasaki equation. This is the equation of perturbations. Okay. I'm not going to the quantization. Actually, you can find it in the literature, how the quantization is done. You can write Rk as an operator. All right. So, and then you operate it on the ground states, and then you calculate the correlation function, R equal time correlation function, Rx prime, Rx prime eta, Rx eta, and you sandwich it between two prime gate states 0, and then you integrate. So that gives you the power spectrum, primordial power spectrum. I'm going to the formula directly, but important thing is that just have a look at the equation. Now, if the sub-Hubble region means that, super Hubble region means that K tends to 0. What does sub-Hubble region means? That means K goes to infinity, or K by H goes to infinity. All right. So lambda becomes very, very smaller than the Hubble's radius. That means K becomes very, very larger. When K becomes very, very larger, you can see very, very large. You can see the K square is very, very greater than Z double prime by Z. You can neglect this term. Then it has a simple solution. Okay. So Vk becomes 1 over square root of 2k times e power minus ik eta. These act as waves, free waves. These are the solution for the free waves. These are called the Bunch-Davies initial conditions. So these are very sacred initial conditions, because at sub-Hubble scales, k square, k goes to infinity. K by h goes to infinity, and then you can neglect those terms. And what you find is that here you automatically end up with the initial condition that you are going to use for the rest of your evolution. For all the modes, for each of the modes, you know what are the initial condition for the perturbation, for the R or V, whatever variable you aim to use. So you start with the initial condition. Those initial condition that you have found, we are going to discuss it in the next lecture with the codes, and then you evolve them up to this point, and then you stop. Then you find the primordial power spectrum or the primordial perturbation spectrum at the end of inflation. Okay, let me see if I'm doing correctly with time. Okay, I might need 10-15 minutes. Okay. So the power spectrum of the scalar perturbations can be written as k cube by twice pi square and rk square at the super Hubble scale, which will be same as the at the end of inflation. There will be very little change, negligible change actually. Simply, this can be written in terms of Mukhanov-Sasaki variable as k cube by twice pi square, because v equal to r times z. Now, if the scalar field rolls slowly, all right, if epsilon is very, very less than 1 all the way to the bottom of the potential till the end of inflation, it can be shown that the spectrum of the scalar perturbations remains very close to constant with a very slight tilt. The tilt will be given by the slope of the potential. Therefore, the tilt is called NS, the spectral tilt, which is written as 1 plus d log ps by d log k. As you can see, if you just take this and take the derivative of the logarithm of the potential with respect to the logarithm of k, you will be able to find the tilt, spectral tilt. Now comes to the tensors. Again, just like the scalars, we can simply write this z00 component and z0i component will be 0. There will be gij component. That will give us the equation for the tensors. Okay, tensor has two polarization, hij. It has two polarization. If you say that this polarization has the amplitude h, both of them have the amplitude h, then you can write the equation of the tensor perturbation. See, this is very similar to the equation of the curvature power spectrum, r double prime z prime, but this is much simpler. Here you had z, which is a phi dot by h. Here you simply have h. You don't have Z. Okay. So when you write this, it comes in a very simple form, k square minus a double prime by a, the scale factor. And then simply the tensor power spectrum can be written like this. This 2 factor comes because of the 2 polarization states of the tensors. So you write the tensor power spectrum like this. Now, let me just define the slow roll parameters, the Hubble slow roll parameters. So the Hubble slow roll parameters is defined as the epsilon 1 equal to minus h dot by h square, I think, and minus hn by h. I'm sorry, the square will not be there. And epsilon I plus 1 is going to be d log epsilon I dn. Okay. So you can see that this epsilon I plus 1, at any iteration, the higher order slow roll parameters, the higher derivatives of the slow roll parameter can be written as the d log epsilon I by dn. All right, just give me a second. Oh, another thing is that I can simply say here that this will equate to phi n square by 2. All right. So this is, and phi n is n equal to d phi by dn. All right. So I made a mistake. This will be minus h square. Okay. So as you can see, that's in terms of the conformal coordinates, conformal time derivative, you can write it as 1 minus h prime by h square. All right. And this is delta h. This is not epsilon 2 or something like that. So you can write it as this value. And in terms of the slow roll parameters, you can write z double prime by z using this formula, a double prime by a. You can understand where I'm going with this. Z double prime by z was present here, scalar perturbation, and a double prime by a was present in the tensor perturbations. So I'm going to solve the tensor perturbation and scalar perturbation equation. When you solve them, when the modes leave the Hubble radius, when k equal to h, sub-Hubble is k very, very greater than h, super-Hubble is, sorry, sub-Hubble is k very, 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 very greater than h, and super-Hubble is k very, very less than h. So, but when the modes leave the Hubble radius, then k equal to h. All right. So the spectrum of the perturbation can be written as h square by twice phi dots whole square, and tensor perturbation can be written as h by twice pi whole square. So this Hubble parameter, the value of the Hubble parameter determines what is the tensor amplitude. Okay, amplitude of the tensor perturbations. As you can see, it is simply h square. If phi remains nearly constant and h remains nearly constant, this, as you can see, the scalar perturbations remains nearly constant. All right. That is why you can write it as an amplitude and a tilt. So if it is just constant, you can write it as an amplitude, just like an amplitude. If it has tilt, you need to take care of the tilt. So it is k to the ns minus 1. K0 is a constant. Okay, so this is a pivot scale to the ns minus 1. And this ns, what is the ns? We have defined it here. 1 plus d log ps d log k. Simply if you basically take the 1 plus d log ps d log k, you will find that it is ns. So you see that the scalar power spectrum and the tensor power spectrum remains both nearly a constant. So therefore, you can also write them with respect to the slow roll parameters. For example, ns becomes 1 minus 4 epsilon h plus delta h, and the tensor tilt nt can be written as minus twice epsilon h. The tensor to scalar ratio, the ratio of the primordial power spectrum primordial tensor to the scalar path spectrum is called tensor to scalar ratio. That turns out to be of the order of 16 epsilon h or minus 8 nt. These are called consistency relations. Okay, so minus 8 nt. So as you can see, nt is twice epsilon h, so minus twice epsilon h. So r becomes 16 epsilon h is equal to minus 8 nt. So this is the consistency relation, as I said. Just a second. And in terms of potential, they look like this. So if your potential is flat, as you can see, your PS and PT will be flat again. And this is the comparison between the analytical calculation for m square phi square model and the numerical calculation. As you can see, if it is slow reloading, you can simply do your analytical calculation and your numerical calculation will be falling on top of each other. What happens is that how we can constrain these models, how we can say that whether large field model is the true model of the universe or the small field model is the true model of inflation, etc. We need to go to the best probe of inflation, which is called the cosmic microwave background, because that is the first light that we can see till now. And we have tremendous amount of information from there. So as you can see, if you get the m square phi square model, you get the primordial path spectrum, then convolve with the transfer function I'm going to discuss in the CMB lecture. That convolution gives you the angular path spectrum. Okay, that angular path spectrum you can also calculate it from the map of the CMB, which I think Professor Twin Ghosh is showing you in today's class, Hill Peaks or something like that, where you can get from the maps to the angular path spectrum. So the angular path spectrum will look like this. From the data will look like this, dots with the error bars. Then you calculate your model. You could take your model and then compare that with the data. As you can see, this is the m square phi square best fit model to the data. As you can see, it is a pretty good fit. This just doesn't have the inflation. It also has omega baryon h squared, so the different other parameters. So you have the baryon acoustic oscillations physics, you have the Sachs-Schulze effect, you have reionization, etc., which comes in to play here. The recombination. So finally, you get this plot, and then you compare with the data. With cosmic microwave background, you have better and better improvement. So we have discussed, right? So the fluctuations in the cosmic microwave background, as you can see, they are of the same order. The power spectrum are of the same order between Kobe and the balloon-based observations. So these are the points that we had observed before WMAP. So WMAP actually got the same thing, but with much less error bar, much precise experiment. So what WMAP did is that it brought down the error bars to an unprecedented level. What Planck did is that it decreased the error bar. At the same time, it also went to much smaller scales. For example, you can see this is of the order of 0.2 degree, right? Now here we went with WMAP up to 0.2 degree, but with Planck we could go up even up to 0.07 degrees. Okay, in the angular scale, we can even resolve smaller and smaller angles. With that, what happens? I'm not going to discuss this part. Okay, so this is something that happened as came as an discovery, but then later it became known as the dust. So yes, now importantly, what happens is that we have different inflationary models, phi to the n, right? I discussed phi to the n. So let's say phi 4, phi 3, phi square, phi 1, and phi to the 2/3. And you compare, you calculate the, and you define your tensor to scalar ratio as R and your power spectrum, scalar power spectrum with an NS, with a tilt of NS. So with WMAP 7, we had this constraint on the NS and R. So it is a pretty big, large bound. So it is not very much constraining. Then we had SPT, South Pole Telescope Observation, combined with WMAP. As you can see, if you have small scale information, you can constrain NS to a very good accurate level, right? So it rejected NS equal to 1. That means a complete scale invariant power spectrum, it rejected. And it found an NS equal to 0.96 as a sweet spot. That means that is 0.96 is something that comes as a mean value. If you add different other observations that actually breaks the residual degeneracies, then you get even better constraint. So how to read this constraint? That means the farther any data point is from these line contours, for example, this is 1 sigma contour, this is 2 sigma. You can keep on drawing the blue lines, fainter blue and blue lines there, and you will see that if you have like this is 2 sigma, and this is scale invariant spectrum at ns equal to 1. That means if you keep on drawing these ellipses, at some point of time, this ellipse is going to cross this one. That means that at that point of time, you can say, let's say you draw 5 ellipses and that touches this ns equal to 1. That means your observation or our observation is able to reject the ns equal to 1 by 5 sigma. Okay. For example, here you see that it is inside the gray line. So it is between 1 to 2 sigma. So it is rejecting by 1 sigma, ns equal to 1. This is more than 2 sigma. This is like 3 sigma. This is of the order of 5 or 6 sigma. So this is the WMAP error. When Planck came, as you can see, again, another thing is that you can see the stand of the inflationary models, phi-4. It is here. It has rejected phi-4, right? It has rejected phi cube. Phi square was here. Then this is phi to the 1, and this is phi to the 2 by 3. Then Planck came, the error bar shrinked a lot. So it observed the microwave background in unprecedented accuracy. And then what you find is that your ns equal to 1 is very, very far away. So even with just with Planck, TTTE, low E, everything I'm going to discuss in the CMB lecture. Okay, I'm going to come back to this plot again. Low E plus lensing, you can simply reject the ns equal to 1 by nearly 8 sigma confidence level. You can find this plot in Planck 2018 constraints on inflation. Okay, as you can see, the phi to the 2 by 3 model, the red model that was there inside the contours, now is outside, right? Phi square model is the yellow one. See what observation does. Phi square model was here, right? Okay, let me get this one. The orange one was the phi square model, so which was inside all of the contours, 2 sigma at least. Now it has gone outside of from all of the models. So phi-4 will be like here. It is rejected. So with the better and better observation, we have been able to put stringent constraints on the model. We have been able to throw away different large-scale model of inflation. The best model now is claimed to be the R square, Stravinsky's R square model of inflation. All right, this is in some okay. Stravinsky's R square model of inflation. I can it is a limit of this alpha attractor model of inflation. You can have a look at the alpha attractor papers as well. All right, so these, as I promised, these are the different models of inflation. So Stravinsky's R plus R square model of inflation is 1 minus exponential minus square root of 2 by 3 phi. Okay, power law potential. So now these are something that I'm going to discuss later, but let me just give you a hint. Delta chi square, if it is large positive, that means that delta chi square is the chi square. Chi square is basically the agreement of a model to a data. That means data minus theory divided by the error whole square. That is called the chi square. Okay, so let's say you have a simple model, R square model, that is matching very well with the data. It is staying at the sweet spot. Then you have, then you have different other models, and you compare the chi-square from the R square, the best model, with respect to others. If the chi-square increases, that means that those models will be less favored or will be rejected. And then you can also compare the Bayesian evidence, which is the marginalized likelihood. Okay, these are something that I might discuss in the CMB lecture. Let me see how I can cover. So if this goes large negative, let's say if it is -5, more than -5, that means that model is rejected. Let's see from here how to read these numbers. This means the power law potential lambda phi-4 has a 75 chi-square worse than the Stravinsky's model. So it is rejected in that sense. Also, it has a Bayesian evidence of -56. If it is -5, then it is rejected. Okay, simply it is rejected. Power law potential phi cube, 44.7 chi-square minus 13 Bayesian evidence, Bayes ratio, okay, logarithm of Bayes ratio minus 13 rejected. So phi linear potential, that also is rejected, minus 3.9. It is moderately, or I think strongly rejected, but not if it is minus 5, then it is evident. And this is minus 4.6. So if you have other models, for example, hilltop quartic model, it is minus 0.3. It is a little bit or marginally better. You can even say that, you can even save the trouble and say this is equal to the Tarminsky model. And it says that it has a, it also has a marginal worse evidence. This one has a marginally better evidence, 0.6, but it is not worth mentioning. Okay, so in Jeffrey scale, you can say that it's not worth mentioning. It has a 2 improvement in fit in the chi-square. It is a 3 improvement in fit in the chi-square with respect to the Starominsky's model in the R plus R square model. Okay, that is the status of the inflationary model with respect to Planck data. Tomorrow, what we are going to do is that tomorrow we are going to discuss the bingo, bispectrum non-Gaussianity operator, but we are not going to talk about non-Gaussianity or the bispectrum. We are going to talk about the power spectrum. We're going to solve the model. We're going to see the background evolution. What is the evolution of phi? What is the evolution of phi dot? The slow roll parameters, etc. And we're going to go do calculate the power spectrum, and then we are going to see how the power spectrum is compared with the data, CMB data, in the next 2 lectures. Okay, so tomorrow we are going to make our hands dirty with the bingo code, and also we are going to calculate the angular diameter distance and the other distances as well. Okay, and your assignment is that for today's lecture is that you can obtain the perturbation equation by solving perturbed version of the perturbed Einstein equations. Okay, so let me minimize and take questions. Stop share. Yeah, please let me know if you have any questions.
Hi, sir.
Yes.
Can you hear me? So, as we know that this space fabric expanded a very large speed, even greater than the speed of light during inflation. So that in a way doesn't carry the information. So can we somehow say that the temperature of the particles that expanded along with the inflation somehow carried the information, like the temperature has some information, right? So would you like to make a comment on this thing?
Yeah, I mean, see, information is not being carried. When you say that it is faster than the speed of light, it is not actually faster than the speed of light, right? Because nobody can, I mean, from one point to the other point, one cannot send a signal. So that is when they become super Hubble. Okay, they become causally disconnected. At some point of time, they again become causal contact, comes in causal contact with each other. So it is not really something going faster than the speed of light. 2 points are receding from each other where causal connection cannot be made. All right, so that is what you can say. So because whenever you say that faster than the speed of light, it is usually associated to the fact that a particle has a speed that is faster than the speed of light, but that is not true in this case. That is not true in any case till now. So yeah, that is the main idea of inflation. As I said, that there was a small ball, let's say we take a tennis ball, which had same temperature inside of all the air molecules. I make it inflate like a football, then like a balloon. Okay, now I know that this balloon from one end to another end, heat cannot transfer in this time, so that basically they have the same temperature. But inflation says that no, they had the same temperature before when they were in causal contact with each other in the ball stage, in the tennis ball stage. Now I have inflated that. So definitely one end doesn't know another end, another end now, but they knew each other before. So they had the same temperature, it inflated, temperature decreased, but they have the same temperature. All right?
Yeah.
Is it clear?
Yes, yes, yes.
Okay.
So I have another question. So
Sure.
for the inflation model, we considered always the scalar fields, like a different part. Why not other fields? Is any other good evidence?
For example, fermionic fields, let's say.
Yes, yes, yeah. So
Fermionic fields are what? They are normal matter, right? Electrons.
yeah.
Yeah. So they are normal matter. So if you solve the normal matter, what do you get for Friedman equation?
I haven't solved.
No. It's simple. I mean, it has a W of 0, right? I mean,
Yes, 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 yes.
The W of 0. So if it is W of 0, normal matter, we discussed, right? It is t power 2/3.
Yeah.
A goes t power 2/3. If A goes t power 2/3, the acceleration is negative. That means
Yes.
P times P minus 1. So if P is 2/3 minus 1, what is that?
Yeah.
Minus 1/3.
Yes, yes.
That means it is decelerating. So you are not able to accelerate with normal matter. You cannot accelerate with photons as well, right?
Yes,
you cannot accelerate with photons. So those particles are out of the question. So only scalar fields can do that. Okay, maybe some complex scalar fields can also do that, but I do not know how successful are they in describing the inflation and the perturbations. For example, as you have seen, first of all, you must need the acceleration, exponential acceleration. So let's say I take the scalar field. Okay, so this is how the story goes. You need an acceleration. So I take a scalar field Lagrangian, but in the Lagrangian there is a potential. With some other potential, you may be fine with the quintessence model or the dark energy model. You can get the today's acceleration with some fields with some potential. But that potential is not sufficient for the early universe, for the inflation. You need a potential where the scalar field slow rolls for the entire 60 folds of inflation, so that you can get, slow roll so that you get the entire amount, the 60 folds or 70 folds of inflation, so that it solves the horizon problem, right?
Yeah.
That fixes the potential. This is background level. So we fix the Lagrangian, we fix the potential. Second step. Third step is that you need to get the power spectrum with the NS very close to 0.96, not 1, not 2, not 0. You need 0.96. That also gives you the slope of the inflationary potential. As you have seen, m square phi square is ruled out. Then there is so m square phi square is not, by the way, m square phi square is not ruled out because of the NS. It is because of the tensor to scalar ratio. Each potential will have its own signature in the tensors. Tensor power spectrum. M square phi square model has a tensor power spectrum, so that the tensor to scalar ratio, tensor to scalar power spectrum ratio is of the order of 0.16. And now today's observation, bicep and Planck observation, gives you a tensor to scalar ratio of 0.06 that is rejected by 2 sigma. So that was 0.16. Even 0.06 is rejected by 2 sigma. So you can understand that 0.16 is rejected by 4 or 5 sigma.
Yeah.
Right? So if 0.6 is 2 sigma, if it is Gaussian, then you can say that 0.12 is multiplied by 2 is 4 sigma. Right?
Yeah.
So again, 1 is, so 0.16 is of the order of, 5 sigma or something like that. Okay, so that means that even it is rejected by 5 sigma significance. Then comes to the other models. When other models gives, for example, R plus R square model of inflation, that their tensor to scalar ratio is of the order of 2 into 10 power minus 3 or something like that, or 5 into 10 power minus 3. I do not exactly know the number right now, but it is of the order of 5 into 10 power minus 3. So in those cases, now we are basically, there is not much room for the models to go back and forth. So we have stringent constraints. We have 60 folds of inflation as a second condition, and the third condition. First condition, as I said, scalar field. Second condition, your potential must give you the right spectral tilt. Third condition, fourth condition is that your potential must give the appropriate tensor to scalar ratio. If tomorrow with upcoming observation, we are able to detect the tensor to scalar ratio by B mode polarization, we will be able to detect the energy scale of inflation as well. So slope we have detected. Next is the energy scale. So if we detect that, then we will not be saying that, okay, today we are going to reject the model. then we will be saying that we have discovered the model of inflation. R is we already discovered NS. Now, if R is discovered, then we can simply say, let's close this chapter. We know what is the model of inflation. Okay.
Yeah.
So that is what we are aiming at. R, for example, for the record, have not been able to we have not been able to find it. There was a discussion, as I said in one slide, that Bicep claimed that we have detected R, but this turned out to be dust. But that was itself a very big contribution to science. There was just we didn't know that dust polarization has such big effect in the tensor in the D mode polarization.
Okay.
Okay. Good question. Thank you.
Yeah. So
Any
I
other
have one or two more questions. Sorry.
Please.
Yeah. So in the perturbation part, we have two type of perturbation, basically adiabatic perturbations and isocurvature perturbations. So for that part, for the CMB and all this, we are just saying that adiabatic perturbations are only like the evidence are only for the adiabatic perturbations. So far there is no strong evidence for the isocurvature perturbations.
Yes.
So what comment do you want to make on this thing? Like
okay. So adiabatic perturbations are coming from single field model. Okay. They don't have isocurvature perturbation. When you have double model, two field model, then you can decompose the perturbations. Okay, in one along the field line and field trajectory and another perpendicular to the field trajectory. It has been shown. I mean, the bingo code that I will be sharing is for single. I have also the two field model bingo code that I solved, where I solved the adiabatic and isocurvature perturbation directly numerically.
Yeah.
It has been shown that for almost all of the models, the adiabatic perturbations become significant at the Hubble crossing, means that when k equal to h, but at the super Hubble scales, they decay, but they leave a firm imprint on the adiabatic perturbations. Okay.
Yeah.
On the curvature perturbation. Isocurvature perturbation decays, but they can leave an imprint. So this is one thing. But if it doesn't leave any imprint, if it was small, then it doesn't affect in any way in the CMB. So perturbations are simply adiabatic that we have been able to establish. If there are large adiabatic perturbations, let's say by some mechanism we are able to do that, there will be large contribution at the large scale TT power spectrum, temperature power spectrum. Okay, so those things have not been found. So then the power spectrum, you have seen that it is flat and then goes high and then has some oscillations, right? If it had large isocurvature perturbations, it would have been some other effects. I think not just there, at smaller scale also it has some strong effects. If I'm able to find some literature of isocurvature perturbations effects on the CMB, I will be able to share what are the exact effects of the isocurvature perturbations at different scales. Okay, but as of now, isocurvature perturbations are consistent with zero as far as the observations suggest. Okay, and another question.
Another question is basically this is said that inflation solves the monopole problem in some sense, that the monopoles, if there were any, that would have been diluted by the inflation.
Yeah.
So like, can we ask that, like, sometime we can hope to find the monopoles if some very precise or something very crude, very calculations that come out in the future? That's time.
Okay, your question is that whether we can find with very precise observation some monopole at some
So basically,
like they're very diluted.
Yeah. So yeah.
Yeah. See, I mean, first of all, this is something that there is a big if. If the monopole had certain density from some theory, then this have been diluted. Let's say the monopole is zero or has very little density, then there is no chance. It depends on whether monopoles exist at what temperature they exist and at what stage of the universe. Which theory says that what is the proportion of the what is the energy density of a monopole before inflation or something like that, right? So this is a question that, for example, just think that omega k is 10 power minus 3, right? Our universe is pretty flat. The question is that if you say that can we detect omega? If the omega was completely zero from the beginning, Okay, there is no chance even in detecting the omega. We have already been able to see that it is 10 power minus 3. If it is 10 power minus 2, then we can say that, okay, the initial omega was this, inflation have been able to dilute this by this much amount, and that's how the omega is there. So first of all, I mean, we have to understand which theory gives, I mean, at what temperature, at what high energies, monopoles are generating from which theory, and then their density, and then from there you can understand whether, for example, it is not like dark matter. It is not like something that you know that there it exists, but you are not able to find it in direct experiments. Okay.
Yeah.
So the thing is that a monopole can be very, very dilute, infinitely diluted, and you will never be able to see that, right?
Okay. Thank you.
Good questions. I mean, any other students can ask me any type of questions, please. I mean, feel free to ask me any questions.
Hi, I have a question. What does it mean that a mode freezes out outside the horizon, and why do modes not freeze out inside out? What's different inside and outside? Because the horizon is just an arbitrary, surface which is limited by the speed of light. So, how does it affect the mode?
No. Horizon is something that is a surface that is limited by the speed of light. That means that you cannot basically be in a causal contact with each other anymore. So when these modes goes, for example, there are certain modes. Let's say gigaparsec, right? We say that there are horizon. We have certain horizon from where we can see. So it is 14 point something gigaparsec, we said, right?
Yeah.
Means 45. What is there beyond 45 gigaparsec? Those modes are outside, right? So they are not in causal contact with each other. So we cannot see that. So that is exactly what is happening there, that those modes were inside, but then went outside. Now it is that there are some modes that are outside. They're still coming inside. So the small scale modes were there that left the Hubble radius at the last and entered first. And the large scale modes entered the Hubble scale first, and they remained for a very, very long time in the super Hubble scale, and then they enter. Yes, what you can understand from here is that the dynamics. So the super Hubble scale, for example, this k square, it is much larger than the phi dot. Okay, so z double prime by z that you have seen there, you can simply say that actually this is a free wave. You start with a free wave when they're very sufficiently subhubble. When they go outside, all right, when they go outside, then k becomes 0. So there is no other effect. So k goes outside the horizon, means lambda becomes very, very large. So lambda with respect to h becomes infinite. So that is why you do not feel any effect there, and the curvature perturbation simply freezes. If you say what is the physical interpretation of that, I mean, you will see, for example, for two field models, it is not true in all cases. It is true only in ideal fluid case, but there can be other things like non-adiabatic pressure perturbations, etc., isocurvature perturbations. In the presence of those, this doesn't happen. There are super Hubble evolution. For example, if you take two field models, there are couplings. In those cases, the couplings can give rise to super Hubble evolution of curvature perturbation. So it is not a given truth or something like that. It is something that we find it to be true for single scalar field models, which behaves like an ideal fluid. Okay.
Yeah, that makes it clear. Thank you.
Okay. Any other question?
Sir, I had a question. So
Sure.
when you were telling about the fermionic or vector-like inflaton models, so those things goes as matter-like or radiation-like when we have a particle distribution kind of thing. But when it is still not particle distribution, something like a field-like, then is there
Then
any other?
also you can write the P and for example, you can write the T mu nu, right?
Mm-hmm.
So at those levels also you can write the T mu nu, and at the quantum level, let's say, you can define the T mu nu, and you can calculate that. So I do not know of any paper that just by fermionic fields people have been able to achieve acceleration. So I mean, if there are people have been able to find, for example, you see the relation is very clear, right? This rho plus 3p has to be less than 0, right? So the phi dot square has to be less than v of phi. So you have to find a potential or somewhere. I mean, even there you can find potentials, vector potentials, etc. And there you have to find in which case it can give you sufficient amount of inflation. As I said, there are several steps. First of all, it has to be scalar field. If you are able to, by chance, you have been able to find some composite scalar field by some other particles, and you are able to achieve inflation, you have to say that it has to have at least 60 folds of inflation. Then the power spectrum, then all the other things will come. So usually, I mean, I have not come across any other things, any other models where you can achieve it with the fermions or vector fields, vector bosons, and things like that.
Okay, sir. Thank you.
Yeah, if you find any literature, please let me know. I will be happy to see and comment on that.
Okay, sir. I didn't find in literature, but I somewhere heard probably some vector like inflaton. I haven't seen those papers, but
Okay.
just I heard somewhere. That is why I was asking.
Sure. No problem. Any other questions? Okay, if you find any questions that, I mean, you do not have in mind right now, but while going through the lecture notes, you come across something and something needs more explanation, just write back to me. You have my email address, I guess. If not, let me just write it down. I mean, let me write. Sure one. So this is my email address. All right. So you just write back to me. Okay, what I'm going to do is that let me also share the copy link, and this is the Jamboard content. So I have made it accessible through the link. So you can just click on the link and go there and see the Jamboard contents as well. So whatever I have written. So if you have any questions from there, please write back to me. Okay. So can I stop today's session? So is there any moderator?
Okay.
You.
Yes. So Sag is not there, so
Sure.
that
No
told
problem.
me to.
No problem. No problem. So should I just leave or what?
Yes. Okay. So thank you for the nice presentation and.
No problem. No. I just said that. To say that. Yeah. No, I just said that whether I can leave now or there are any other questions that you have to ask. I mean, sorry, you need to ask or something like that.
Okay. So if there is no other questions, then probably we may leave and.
Yeah. So tomorrow we are going to meet, right? And please just download that. Everybody has access to the workshop ISI folder, right?
Yes.
Okay.
Yes,
You
but
have been able to
I think
download.
in the Psi server folder we cannot download the whole folder probably. We are only being able to download the files separately. So if you have some zip file, probably you can upload it and then we can
Oh, is
download
that
it.
so? I didn't know that. So, okay. So tomorrow's lecture, the thing that is needed is Bingo. Okay. And another one that will come as a IPython notebook. So Bingo one, I will make a zip and then I will just let you know what needs to be downloaded. Okay.
Okay.
iServer already has G Fortran, so there is nothing else needed to be installed. Okay. So,
Okay.
all right. All right then. Okay. See you tomorrow. Bye.
Okay. Fine. Okay, so let's meet on the second session. Please come everyone before 10 minutes of the scheduled time so that we can start it time. And okay, bye everyone.